numerical evolution of five-dimensional asymptotically AdS spacetime.
Okay, thank you. And thank you to the organizers for the invitation to come and talk here. So can everyone hear me? Is this on? Okay. So first of all, I want to apologize to those of you that have seen this talk and this work before. Unfortunately, some of the stuff that we've been working on the last little while isn't yet ready for to show as results. So this is an old talk. Hopefully there are people in the audience that haven't seen this before, but I apologize to those that have. So again, I'm going to talk about some work that we've been doing in the last few years with, whoa, okay, bad idea. With a grad student who's now graduated, Hans at Princeton. And this is mostly his work. This is formerly his thesis, so you really should get most of the credit for this. And Steve Gupser. And it's about simulating in solving the Einstein field equations numerically in asymptotically five-dimensional anti-de Sitter space. So the outline of the talk, I'll give a very, very brief motivation. I suspect everyone here knows exactly why we're interested in this subject. I'll give a very brief motivation. And then for the lion's share of the talk, I'll sort of split it up into two pieces. The first bit, I will describe our approach to numerical solution of asymptotically anti-de Sitter spacetime. In particular, this generalized harmonic evolution with constraint damping. So as I'll mention, the motivational, one of our early goals was to apply this to heavy ion collisions by using the AdS CFT to look at gravity and apply that to say something about heavy ion collisions, quark-gluon plasma formation. We're very far from there in terms of what one would need in a code. And so in this sort of as a preliminary sort of warm-up project, we looked at the nonlinear phase of quasi-normal ring down of black holes. And so I'll show in the second part, I'll show some results from that. In particular, looking at very distorted black holes. So that's one of the advantages of numerics, is we don't have to restrict ourselves to perturbations. We can look at very large nonlinear effects. And so one of the things is we can ask, well, how well does hydrodynamics still behave when we look at black holes, or this hydrodynamic limit when we are very far from the perturbative regime. Okay, so my one slide motivation, again, we want to explore aspects of the AdS CFT correspondence, the gauge gravity duality. And where I come into this game is I'm a numerical relativist, so that's my area of expertise. And so I'm more interested in understanding the gravitational side of this correspondence in the limit where Einstein's gravity is a good description to the bulk dynamics. So the large and strongly coupled CFT limit. Another reason for, as I mentioned before, bringing numerics into this is we aren't restricted to looking at situations with symmetries, even though I'm going to be showing you, for practical purposes, symmetry reduced spacetimes in this example. But in principle, we aren't restricted to the imposition of any symmetries or any special simplifying assumptions in initial conditions, nor perturbative conditions perturbing around black holes. We can look at full nonlinear dynamics. And eventually we'd like to apply this code to many things, but the initial goal was to look at geometries that are dual to, or hypothesized to be dual to, quark-gluon plasma formation in heavy ion collisions. Okay, so let me sort of describe the motivation for the particular approach that we've taken. And the first thing that we decided to do several years ago is to write a code that could solve in asymptotic anti-de Sitter spacetimes in global coordinates. So you have written the metric of AdS spacetime in global coordinates. You have sort of a diagram showing that's so the conformal structure of it. So this is time, the vertical axis. Here's a radial direction. Two of the angular coordinates have been suppressed, and this is the boundary. So in these global coordinates, the boundary is conformal to the Einstein static universe. Now, of course, for most applications, in particular relativistic heavy ion collisions, we're interested in the Poincare wedge, or in particular the Poincare patch on the boundary, so the Minkowski space, or conformal to Minkowski space. But the reason that we wanted to use global coordinates is eventually we do want to apply this code to other problems. We don't necessarily want to be restricted to the Poincare wedge. And one advantage of using global coordinates is that we can do both. We can evolve something in global coordinates and then just extract a little Poincare wedge out of the results at the end. I'll show you an example of that towards the end. So it's sort of a more flexible sort of framework to start from. So the goal is to numerically solve the Einstein equations in the space-time coupled to some form of matter. In this case, we're going to just look at a massless scalar field, in fact, no potential at all. So these are the field equations, cosmological constant, stress energy tensor of the scalar field. And we're going to use the generalized harmonic scheme with constrained damping, which I'll explain a little bit in the next slide. Now, just want to make one comment. It's in a sense the relevant degrees of freedom that we're looking at in terms with respect to the AdS CFT correspondence here is just purely gravitational degrees of freedom. We're not going to be putting any expectation value for this on the boundary or introducing various operator insertions. What this scalar field is going to be is just purely a vehicle to create black holes that we can then evolve, and I'll show you this. I'll demonstrate that a little bit later. So right now you can really think of it, we're pretty much looking at vacuum black holes with a scalar field as a device to create the black holes. So this is a kind of a complicated, messy slide. There are a few key things that I want to describe about this generalized harmonic evolution for those of you that have not seen this before. So one problem with Einstein equations, at least, going from this very nice tensorial form to something that we can discretize and solve on computers, is in general it doesn't have a well-defined mathematical structure. You have to massage it to get it into a form where you can actually discretize it. And one way of doing that has been very successful numerically, and it's this dates back to analytical work decades ago, is harmonic coordinates. In particular, with harmonic coordinates, what you do is you impose a condition that for each coordinate, the covariant wave operator acting on the coordinate is 0. Generalized harmonic refers you can add a source function. So box x equals h. And so when you take that condition and you substitute it into the Einstein equations, and you then say, well, let's treat these source functions as independent functions, then what that does to the Einstein equations is it converts it into a set of manifestly hyperbolic equations. And that's what this was supposed to demonstrate. So this is the Einstein tensor with this substitution in. And the important thing to focus on is the principal part of this equation. This is just the principal part of the scalar wave operator acting on each metric element. These are all lower order terms. They only contain first derivatives. So the nice thing about harmonic coordinates is, at least for the principal part of the field equations, you just get a set of linear wave equations. All the nonlinearities and the couplings are in the lower order terms. So this puts the field equations in a form which is very nice to work with, both analytically and numerically. One comment, though, is, as I said, we've now promoted these to sort of independent functions. So in some sense, we've expanded the system. We're looking at a larger class of possible solutions to the system now of this equation and with these source functions than just Einstein's equation. And of course, we aren't interested in this larger class of solutions. We're only interested in the set where this actually vanishes. So that's why these C's, we can think of them as constraints. In fact, these are related to the more traditional Hamiltonian momentum constraints from the ADM formalism. So we've got a larger system of equations, but we're only interested in the subset which satisfies this constraint. Now, thanks to properties of the Einstein equations, the Bianchi identities, etc., it turns out that if you choose the initial conditions in a Cauchy evolution where this is satisfied and your boundary conditions are consistent with that, then evolution is going to preserve this constraint with time. The problem with numerics is when you discretize these equations, you introduce truncation error, and the truncation error is not going to satisfy these constraints. So any numerical scheme, you're going to introduce violations of this constraint. Now that's not a priori a problem, but it turned out, and this is what numerical relativists have spent a couple of decades trying to sort out, is that in most ways of writing the field equations, including this generalized harmonic form, those constraint violations grow exponentially. And that will very quickly spoil any kind of answer that you're trying to get out of the code. And so a key ingredient in this formalism that Carsten Gundlach and various other people introduced is a so-called constraint damping. And that's this set of terms here. I don't want to sort of go into the details, but just to point out that this is an important addition that we're adding to the field equations. But you can see that it's homogeneous in these constraints. So any solution to the field equations as c equals 0. So we're essentially adding nothing to the solution. But the important thing with numerically is if we do have a small constraint violation, then at least empirically, it hasn't been proven in general situations, but empirically, it turns what are exponentially growing modes into exponentially decaying modes. And that's why it's called constraint damping. So these terms are crucial for long-term stability of numerical codes. Okay, so that's the formalism that we decided to choose. And the reason several years ago that we decided to go by this way is just because of its success in asymptotically flat spacetimes. As I'll explain in a few minutes, there turned out to be some serious headaches in asymptotically anti-de Sitter space. And there have been other methods, like the characteristic method that Paul and other people are going to be talking about, that is perhaps better adapted to certain kinds of problems. But in any case, our original motivation was how well this worked in asymptotically flat. Well, let's just try it in this case. And of course, the difference is the boundary, and the boundary turned out to be a big nightmare. So let me just quickly first introduce the specific coordinates that we're going to use. So this is AdS 5, but again, just for computational efficiency and to take sort of baby steps to get to the full problem, we're going to look at axisymmetric spacetimes to begin with. So we're going to introduce this set of coordinates, time, a radial coordinate, 3 angular coordinates. We're going to have an SO3 symmetry, so it's really the solutions are only going to depend on t, rho, and chi. We're going to compactify. R is the usual radial coordinate if you're going from 0 to infinity. Rho is going to be our compactified one going from, so that we can include the outer boundary on the finite domain. And just to illustrate, this is what AdS looks like in these coordinates. And just another variable that I'll be using next is a sort of Q variable. That's sort of a variable that measures the distance from the boundary. So the difficulty with the boundaries stems, well, part just from the physics of the situation, and just sort of very schematically we can sort of think about solutions to the field equations in this kind of space-time. We can sort of write it in this form. So we want to solve for the metric. And if we sort of do an expansion in terms of this Q variable, this distance to the boundary, there's a singular piece which sort of depends on our choice of the background metric. And then there's sort of the dynamical bit, the part that's going to come from the solution comes in at a lower order in this Q. So this, I'm going to sort of call this background dynamical. It's not, perhaps not the best choice of words, but the key point is this is something that we can choose. So for example, we want the boundary, so the limit Q equals 0, we want it to be conformal to Minkowski space, for example. So that sets the background. There are many different choices. But the key thing is that you can choose. And then we specify some initial conditions in the interior, we evolve it, and where all the interesting results are that are relevant in this AdS-CFT dictionary is in this part of the solution we're calling dynamical. It doesn't have to be dynamical, you can look at static situations, but this is where sort of the interesting dynamics comes from. And this we don't choose. So the difficulties in this, to dealing with this numerically is, okay, we want this metric here, but it's singular. We need the boundary, but we have a 1 over Q squared here. So in some sense, we want to define variables where we're really only looking at this dynamical part, this bit that's interesting. Because this we choose, it's fixed. This is the boundary condition. This is what we're going to get from solving Einstein equations. But the one sort of problem, if you just naively said, well, let's do this factorization. Let's use this as our dynamical variable. We have a set of PDEs. We want to pose a well-posed initial boundary value problem. Because this is really our boundary condition, we can't really specify boundary values for these dynamical variables. That's going to come from the solution in the bulk. I mean, that's really the physics of AdS-CFT. We said this is sort of the boundary, what's going to happen in the bulk, how the metric is going to fluctuate approaching the bulk. That's going to give us all the things we're interested in. We can't put that in by hand. And perhaps another way of saying it from the numerical perspective, you've got a set of PDEs that you've discretized, and at a boundary, you do a characteristic decomposition. If you want a stable evolution, you can only place boundary conditions on characteristics that are coming into the domain. And moreover, you have to place boundary conditions on those characteristics. And so if you look at the sort of the physical characteristics in this kind of decomposition, then there are no characteristics coming into the domain. So there are no boundary conditions that you can place on these variables. So to sort of summarize the solution, one trick to do that is we don't want to use this as our dynamical variable. We essentially want Q times this as our dynamical variable, and then we can put a Dirichlet condition on that combination. And that's sort of a trick to effectively not put a boundary condition on the dynamics that we're interested in. So this is sort of what we do. So we take the background piece. This is where the interesting dynamics is, and we have to do the same with the source functions. We want to choose coordinates that are Pfefferman Graham-like as we approach the boundary. I mean, there is coordinate freedom to choose your radial coordinate like you want, and that's what we want to do. And then if we look at this, in these coordinates, this particular decomposition, this is the results for our, for the particular metric with this, the t, rho, and chi coordinates. So again, so these barred variables are the ones that we actually discretize in the code. This is the unbarred variables, that's the full metric. This is the background bit, and here we've multiplied it by sufficient powers of Q, such that each one of these variables is a simple Dirichlet condition. They all go to 0 on Q as the boundary, and the same with the source functions and the scalar field. The other factors of 1 minus rho is just for regularity on the axis, because again, in this first study we're looking at axisymmetric spacetimes, and we also have to deal with the axis. Okay, so a little bit messy, but okay, you just do this, and I mean the computer does most of the work. So that's what we hoped. Well, we did this, and things would be solved. But it turns out to be a little bit more tricky in the harmonic formulation. And this is something which, unfortunately, I don't really understand exactly why we need these extra conditions. But it turns out that that's not enough for stable evolution. And basically, the problem is, so we've factored out all of the correct powers such that those variables are regular. You can think of these source functions as encoding coordinate degrees of freedom. They're sort of the equivalent of the lapse and the shift in the ADM formalism. So you'd think, well, okay, we can freely specify them modulo all these factors that we've extracted for regularity. But it turns out that a generic evolution equation for these does not preserve those regularity conditions, and they tend to become singular. And so, sort of by trial and error, we sort of found that we have to impose asymptotically these restriction relationships between what we thought were free source functions and the asymptotic values of the metric. And I emphasize these are the regular variables, so these are the leading order pieces that we think we should be able to freely specify. And I emphasize these are not the constraints. There's some additional structure that has to be imposed in this generalized harmonic scheme to get stable evolution. I don't have a deeper understanding. There probably is a good way to think about it. And the problem by not having a deeper understanding is we had to come up with this by trial and error, basically, which means, and that's why new results have been sort of slow in coming, because we want to now add operators on the boundary. We want to look at different kinds of boundaries. But with every little change we do, we have to go through this process again. We have to do a near boundary expansion of the field equations and sort of guess what these conditions are. This is not a unique set in this case. There are other options which may work, and again, they're not the constraints or the evolution equations. It's just it's something that unfortunately I don't have a good explanation for.
So Frans, you emphasize that you need these for stable numerical evolution. Should I understand then that you believe that if you were solving the equations exactly, analytically, or some such things in a generalized harmonic gauge, these conditions would not be necessary, or you think they would still be?
I think they would. But it's difficult to be conclusive in a numerical scheme if things go to hell. Do they go to hell because they're being? So what I think is happening. So in some sense, we've done this particular decomposition. We factored out these powers, and in this decomposition, so these are regular, but with the general gauge, so now you have to, I haven't specified like what we do for these evolution, but you specify some set of equations for those source functions. And there's nothing that says that these pieces don't develop 1 over Q type behavior. So that's still, it's still fine, but in some sense we want to keep this kind of factorization during evolution. And this is what I think, that it's just not good enough just to do this separation. But I mean, that's just the guess, and there might be a deep reason. It might actually just be some numerical problem with the way that we've done it, but at least this is. And actually, sorry. Right, so that I don't think it's numerical, but there are a couple of if you do this near boundary expansion, there are a couple of places where you see, in some sense, where this sort of where you actually have to apply it. I said there's a little bit of freedom with some of them, but there's a couple of equations where a couple of these conditions, like this one in particular, there's no choice. And so I think that's telling us that there's something deeper to this, that even at the analytical level, you would have to choose conditions that enforce that. Okay, so sort of the bottom line, sort of spending so much time on this little piece of it is, I think for those of you that sort of want to write numerical codes, I think there are lots of advantages to this generalized harmonic scheme, a Cauchy type evolution in global, but there are also some serious headaches. I think like, for example, stuff that Paul and people have done with the characteristics, and that seems to be a hammer that's very well suited to a set of problems, and it's perhaps a much better approach to start with. But if this is the way that you want to go, there are some issues that still need to be resolved. It's not a completely everything that I said before, the generalized harmonics, the constrained damping, factoring out these things, I think that's perfectly well systematic. This is one bit that's still a little bit unsatisfactory. Okay, I'm not going to say much about the code. We just use finite difference methods, second order. We find apparent horizons with the flow method, add dissipation, etc. If people are interested in the numeric, just ask me. Okay, so let me just, the last half of the talk then show some of the results. So again, I mentioned with initial data, well, what we're going to do is, okay, so that we'll have a sort of a facsimile of an approximation to some heavy ion problem. So you've got two heavy ions that smash together. Most of the particles just sort of pass through. There's a little bit of the quark gluon mess that's left behind. It eventually thermalizes, and then you get what's thought to be a hydrodynamic expansion, but eventually hadronizes. And then the various experiments see the hadrons that come off from that. So ideally, it would be great if there could be sort of an ab initio simulation from the beginning, with all the various caveats about applying one of these conformal field theories. But the kind of initial conditions that we're going to look at, we're going to look at sort of pancaked distributions of scalar field energy that's going to form initially black holes that have a similar shape. And so if you think, well, black holes are sort of thermal states. So in some sense, what we're doing is we're starting at a point post-collision and post-thermalization. So that's sort of perhaps if you eventually, well, we're not going to say much more than that, but that's sort of the closest that we can, with this code, come to, then if we wanted to model heavy ion collisions. So we're going to take a scalar field distribution. That's going to be time symmetric, so that's again another approximation which is not quite accurate for that stage of it. And then we're going to let it evolve and see what happens. So what this just shows is that, well, we can find trapped surfaces in the initial data. So we take a distribution, a Gaussian distribution of scalar field. Again, it's not relevant at the boundary, it's just a device to create black holes. As we crank up the amplitude, at some point, so this is the asymptotic mass as a function of the amplitude. At some point where the black circles come in, we find trapped surfaces in the initial data. And this just shows that the mass of the trapped surface as measured by the area is very close to the asymptotic mass. And as we go to large amplitudes, it actually becomes the same. So we form black holes using distributions of scalar field. So the first thing that we can do is, well, let's look at quasi-normal ring down of these black holes. So we form a distorted black hole. We expect that it's going to ring down by a set of damped sinusoids to an AdS Schwarzschild black hole. See, there's been a lot of work on quasi-normal modes of black holes. I guess the only comment I want to make here is because of the symmetries. So you can sort of decompose the perturbations of the metric into vector, scalar, and tensor modes. But because of our symmetries, we can only excite the scalar modes of the black hole. For the scalar modes, for the gravitational degrees of freedom, there's so-called fast and slow modes. And the fast modes are fast. If you look at the radius of the horizon, the fast modes scale with the radius of the horizon. The slow modes, these are perhaps the ones that are more familiar with asymptotically flat black holes. They're inversely proportional to the size of the black holes. Perhaps you'll look at these fast modes you might want to associate with microscopic degrees of freedom on the boundary, whereas the slow modes are hydrodynamic. And the scalar field only has fast modes. So let me show you an example. So this is sort of a depiction of a solution of a numerical solution. So this is a slice of global AdS. This is rho equals 0. This is rho equals 1. So this is the boundary. This is the axis. So if you want to think of the actual distribution, just sort of spin this around this axis. So this plot is showing the magnitude of the scalar field. And here, to create a distorted black hole, so we're putting up a Gaussian, and then we're distorting it in the x and y. There's a relative distortion, sort of flattening in the x versus y direction, controlled by this wx and wy parameter. So you can see here it's sort of slightly pancake. So this is the initial data. There's actually a trapped surface here. So when I play this animation, you'll see this sort of like black sphere appear, and that's our excision sphere. So we find the apparent horizon, and to get rid of the singularities inside the black hole, some distance inside, we cut out the computational domain. So the actual horizon is a little bit outside that black region. So let me play this. So you can see what happens with the scalar field is that it rings down. And with this animation, we're continuously rescaling the amplitude, so it's at a constant value. But if you look at the scale here, it actually is exponentially decreasing. And just one interesting thing with the scalar field, again, this is irrelevant for the dynamics that we're interested in. It's getting, it's incredibly small here, so it's not really having a dynamical effect here. But this sort of ties into this turbulent instability that Bizon and other people are probably going to be talking about at this conference. But the interesting thing with these modes in AdS is the large angular modes decay more slowly than the low angular modes, and that's why you sort of see this sort of structure forming at late times. I mean, the amplitude's becoming very small. And what all of that really means is in our initial data, we have this squashed Gaussian. So we've got an infinite sum of even L modes. The initial amplitude of the small L modes are much higher, and that's why you see them in the beginning, but they decay more rapidly. And so with time, you see the higher L modes start to appear.
Can you plan to see this again? Yes.
Sure. Okay. So they're the smaller L modes that are more prominent in the initial data, but now with time they decay more rapidly, and so you start to see the higher L modes come in. Okay, it is kind of psychedelic, but okay. Now, for the same animation, I'm just going to show you one of the metric components. So this is now going to ring down to a Schwarzschild black hole. The difference here is it's going to settle down to something of order unity, and then these, what's sort of plotted here, the quasi-normal modes is going to be sort of an oscillation on top of that. Right, so it settles down to, at least in this coordinate system, this particular component, one of the angular components, what it is in Schwarzschild. You can see very rapidly it settles down to stationary state.
So what's black here is what's inside the apparent horizon?
Yes. So inside the excision surface. So the apparent horizon is about 10% larger, but it's got the same shape, it's just a little bit larger.
Wait, is this the same shape even when it's very distant?
Yes, but it's an approximation. Well, no, sorry. No. It's the best fit sphere. So we take the yes. Well, sorry, I was thinking of another problem. So it's the best fit sphere, and then so we find the shape of the apparent horizon. We find the largest encompassing sphere, and then we use that to define the excision surface. In fact, let me just show you the next picture. It's definitely not circular. Because there's the one promise was we were going to be able to look at the nonlinear regime of quasi-normal modes, and just to demonstrate that we really are in the nonlinear regime, this is plotting the equatorial to polar circumference of the horizon as a function of time. And of course, if you add a sphere, it's going to be y. I mean, imagine if you flatten this thing down to a disk, it should be pi by 2. So in the most extreme case that we've looked at, this ratio is 32. It's initially at over 2, which means that we've distorted this geometry so much that, I guess, negative hyperbolic curvature is developing on the intrinsic geometry. So you can, in a simple way, even embed that in a flat space. So we're looking at very distorted black holes to begin with. I'm not going to show you sort of the decomposition in terms of quasi-normal mode. I'm now just going to sort of jump to the hydrodynamic description. But even in the quasi-normal modes, from essentially this initial time, well, the distortion of the metric looks like a sum of quasi-normal modes. The only nonlinearity that we see is a mode coupling between the two. So if we sort of produce a higher order mode, but it's surprisingly well described by quasi-normal modes. And you'll see that actually with the hydrodynamics. So what we want to do now is take one of those simulations, apply this AdS CFT dictionary, compute the stress tensor of the CFT on the boundary, and then we want to, well, I'll just show you that, but one couple of questions that we can ask is, how well is it described by hydrodynamics? So just one comment that, because we use in global AdS, with the S3 topology on the boundary, even in AdS space, there's sort of a Casimir component to the stress energy tensor, and we just subtract it out. So this is sort of the usual prescription, but if you do it in Minkowski space, you don't need this, but because we're doing global, we subtract out that Casimir contribution. And this is the expression for the stress tensor. So this is what we get. So I'm just showing you a couple of examples of two components of the stress tensor. So this is sort of the energy density. This is a pressure in this one angular coordinate, this chi coordinate. So time is the vertical axis, and here is this angular coordinate. So this is a sort of a moderately deformed case. And so what you can sort of see here with the energy density is there's more energy density on the equator of the boundary, there's less on the poles, and then it sloshes around and eventually settles down to a stationary state, which well approximates what you'd expect from the exact analytic AdS Schwarzschild solution. So this is the reflection on the boundary of the quasi-normal ring down of the space-time. Yeah. I think it's the speed of light. I believe so. I don't think it's the speed of sound. So I'll show you the plots of the velocities later. So in this case, the maximum velocities are about 0.1. In this most extreme case, it's close to the sound speed of 1/√3, but it's not quite there. But I think if you look at like what's the light crossing time of AdS, it's really following these little triangles. So I think that's in some sense it's not physically that the fluid particles aren't going at the speed of light, but it's just the initial conditions that we're setting up until this projection, at least in global. And this is the largest asymmetric case. So again, so now we have, I guess the scale doesn't matter, it's just the ratio. I've got a much larger concentration of energy on the axis, very little on the poles, but again, it sort of sloshes around as it brings down to the stationary state. Okay, so now, so we can we just use that prescription to extract the stress tensor at some set of numbers. Well, what does it mean? Perhaps perhaps the most interesting thing to try to compare it to is that of a conformal fluid, and see, well, is it behaving like a hydrodynamic fluid? And the way that we're going to test it is we're going to sort of use this hydrodynamic expansion of the stress tensor. So this is sort of an expansion of the stress tensor in the velocity and velocity gradients of the flow. So, so the leading order piece, this is ideal hydrodynamics. So this is the energy density, this is the full velocity of the flow, the pressure, this is the projection tensor. The next order, there you get the viscous terms. So this is the the shear tensor, the viscous term. To second order, you get all these additional terms depending on various gradients of the velocity flow. And all those, the transport coefficients have been computed using this AdS CFT up to second order, I believe. And this is the results from the literature. So if you're in a phase where hydrodynamics is a good description, then this expansion should be valid. And so we want to compare what we get with this expansion. And so the way we're going to do it is as follows. Well, the first thing is, regardless of the expansion, what order we compare it up to, we better get conservation of stress energy, and it's a conformal fluid, so the trace better vanish. And we did check that. And with the numerical truncation error, that is true. But so to compare it to that expansion, what we're going to do is at each point on the boundary, we're going to extract the energy density and the fall velocity. So here's just an angular fall velocity. And so from that, we can construct, from the fall velocity, we can construct any one of these gradient terms. So we've got the energy density, we've got the fall velocity, and then we're going to use these constitutive relationships to reconstruct order by order the stress tension and compare it to what we actually get. So anyway, let me just show you the velocities before I show you the results. So this is the two different cases. As I mentioned before, so in this particular case, the velocities are perhaps most 12% the speed of light. In this case, it's about half the speed of light. And interesting, so we have, it's very difficult, for whatever reason, things become very difficult when we try to go to larger asymmetries. And we haven't yet been able to get to a place where we get these velocities to be the sound speed. I mean, again, this though is not sound waves. I don't think it's right to think of these as sound waves. I mean, of course, bulk flow can have a velocity that's larger than the sound speed, but I'm not sure why we haven't been able to go above that. That's perhaps unrelated. But in any case, this is the velocities. So we have the velocity. I showed you the energy density in the previous slides. And so here's the results of the comparison. Let's just focus on this most extreme case, and let me sort of explain what we've done here. So this is time. And here what we're doing is, so this goes up to 2.5. So I just want to show you that going back to this plot of the distorted horizon. So that's about this little time segment. So that's going to correspond to this piece where, at least in the bulk, things are very, very far from equilibrium. So what we've done, in this top diagram, we've extracted the energy density and the velocity, and then we've computed the first order term in this gradient expansion. That was the ideal fluid stress tensor, and we've subtracted that from the actual stress tensor that we measure on the boundary. And this is the difference between that normalized by the energy density. So the black curve in the middle is the result from our highest resolution simulation, and the gray regions around is an estimate of the truncation error from convergence studies. So that's sort of the uncertainty in our simulation. And so what this plot is showing you is this does not look like an ideal fluid, but it's actually not too bad. I mean, the relative difference is at most about 3%. So even in this very highly distorted case, ideal hydrodynamics isn't such a bad description. Now what we do here is now we say, well, let's take the ideal part, add the viscous term. So going up to the next term in expansion, you can see the improvement becomes better. If we go to second order, it's at most, except for this initial gauge transient, but essentially from close to t equals 0, it's about within 0.5% of the expansion. Which I think it's pretty remarkable that in such a case, which is such a extreme distortion of an AdS watch, of what eventually settles down to an AdS Schwarzschild black hole, this hydrodynamic expansion is really showing what's happening on the boundary. Yeah.
How big was the black hole in AdS in the final black hole?
This might have been 5, I think. Either 5 or 12. So we did a range between that. And I think the examples, I forget now, we focused on one of those two. Yeah.
The energy density is not uniform in our thing. So you're looking at local, when you compare with the expected thermodynamic result, you're assuming sort of local thermodynamic equilibrium at each point.
Yeah. So this is a norm over the angular. So we're doing this comparison at each angular point, and then we're taking a norm over it. And so that's a good point. So I think what this is sort of, I think, telling us, and especially years back in the literature, I think there was this a notion that in applications to heavy ion collisions, that the quasi-normal ring down time was somehow associated with thermalization time. But I think what this shows, and what people have pointed out before, is that this is more associated with isotropization or homogenization or hydroization time. Actually, no, that's not quite right. So, because this is, in some sense, what we're saying is we're starting with a black hole. It's very distorted, and so what it's projecting to is a very inhomogeneous state for the initial fluid, but we're still in a description with a fluid. We're still in a regime where the fluid description is valid. And so what this ring down is corresponding to is just the homogenization of this fluid. So even it's a very good description of hydrodynamics. Okay, so the last thing that I want to just quickly show is that was the global solution, but just well, we can also then extract a little Poincare wedge and show you what might happen in a Minkowski segment. So at least the most naive conformal mapping that you can do, we have axisymmetric bulk simulation, so that will correspond to sort of spherically symmetric flows on the boundary. But if you're a little bit more, well, if you're Steve Gupser and you're a bit more clever about these special conformal transformations, you can actually get the conformal transformation to do a lot of work for you. So even though there's in some sense only one relevant non-trivial dimension, this angular dimension, with a special conformal transformation, you can sort of get a little bit more out of it. So I won't go into more details about that. I didn't quite understand this transformation myself, so you can ask Steve. I think he's not here yet, but I think he'll be here at the end of the week. But in any case, so this is sort of a half of the Poincare wedge, because we're starting at t equals 0. So this little piece, applying the conformal transformation, I'm just going to show you what so this is the temperature looks like of that first piece. And it's perhaps not too surprising. So this is the initial state. So you can sort of think this is an approximation of this just after thermalization. And not surprisingly, it sort of just expands and dissipates away. Okay, so to conclude, of course, there's a lot more that needs to be done. Even if we just wanted to take this first step and perhaps try to apply it to the LHC, we'd want to connect it to some particle production hadronization scheme. Of course, this doesn't have confinement, so it's not going to. It's just going to be sort of the high hadrodynamics. Of course, we want to relax symmetry, so we can actually. The next step would be relaxing one step of symmetry, so we can look at central collisions, and eventually, this might be a few years down the road, but the full 5-dimensional problem, so we can look at non-central collisions. As I mentioned in the beginning, one reason for using global coordinates was that we could study other problems. And so adding various kinds of matter to perhaps start looking at some of the interesting condensed matter applications that people have mentioned, or looking at just some issues of pure theory, such as the turbulent instability away from spherical symmetry. Thank you.
Questions?
Yeah, it's related to one of these conclusions. So from a technical point of view, how difficult is it really to relax symmetry? Is make the problem much more difficult?
So the best case is it's just that the computer has to work harder.
Okay.
And so going to one more symmetry, it'd be a 3+1 dimensional simulation. That's something that I think is pretty easy to do today. With Paul's methods on a desktop with these kind of Cauchy codes, you need a cluster, a few hundred CPUs. I'm going there. The final step, it'd probably be a few thousand CPUs that you'd need to put on the problem. So something that would be difficult today. The thing that's less trivial, and I think that the biggest problem would be the boundary conditions that I mentioned. So, the fact that we don't quite understand why we have to set those connections, those relationships between the source functions and the metric. I don't know how it's going to how that piece of it is going to change as we relax the symmetries. And I can anticipate that that's going to be the most challenging thing going forward.
On that vein, if you did AdS 4,
Yeah.
it's naively, I mean, it's a much lower dimension. Easier. Is that, did you?
We haven't tried that yet, but that would be sort of the same. And something AdS 4 is something that could, in principle, be done today. Be slightly different conditions, but I'm not sure if. Yeah, because I'm not 100% sure exactly what's going on. I'm not sure if the dimension plays any factor into what these boundary conditions are. But again, I suspect that will be where the problems, where some work will have to be done.
Let's thank Frans Pretorius.